Okay, so um, we're going to start off with the very, very, very first lesson where we talked about, where we introduced static electricity. And static electricity, I mean, it's the first third of the entire course had to deal with static electricity. So it was important to define what static electricity was. If you guys remember, it's basically anything where there's no movement of charge. But that's also a little bit of a lie because we did some movements of charge in static electricity, and I'll remind you guys about what they were. Um, there are some very basic principles that I mean, you guys, I wrote them here, but I don't know if it even needs to be said almost. It's so like, it should be so ingrained in you guys. Like, do you need to go home and memorize that opposite charges attract and that similar charges repel? No, that's kind of like second nature at this point um, for you guys. I think even before coming into this course, you guys knew that. The important part of static electricity is knowing that there is no steady flow of charges. Okay, so there might be the movement of one charge, because we talked about that. We talked about how if you put a charge in an electric field, that charge is going to move. But what's important is that there is no steady flow of charges. All right. And when I'm talking about a steady flow of charges, I'm talking about a current. So it's going to be many charges flowing at some rates, and that rate does not change as a function of time. That would be what's considered to be a current. Just the principle of net charge is also important. So that's quite simple. You take your positive charges, you subtract your negative charges, and you have your net charge. So for example, if I have a chlorine atom that has eight protons. Oh, sorry, how many protons does chlorine have? What's the atomic number of chlorine? 35.45, so that's 17, yeah. So 17, chlorine has got an atomic number of 17, therefore it's got 17 protons, and if it had 18 electrons, then its net charge would be minus 1. Okay, good. What's that? Okay. So that's that. So that's basically finding the net charge or the balanced charge of anything. Right? So positives minus negatives. There's three ways to charge an object. If you guys remember, there was friction, induction, and conduction. And I mean, it's all about applying these three methods to solving how something becomes charged. And remember, we used this series, this chart called the triboelectric series, to see if two things were rubbed together, which one is going to become positive, which one's going to become negative. So I have a question for you guys. It's going to require a triboelectric series. So if you have your computers open, just pull one up. Um, so the question is, on a cold Christmas morning, you walk down your carpeted stairs in your wool socks and open a present that is filled with styrofoam packing bubbles. I mean, it's not just styrofoam packing bubbles. There's actually a gift in there. You're annoyed to find that everything is sticking to you. All the styrofoam is sticking to you. Explain why they're sticking to you and how you could make it so that they won't stick to you. You might need to pull up a triboelectric series for this. Is Elizabeth coming today? You look at wool and you see how high is it on the list. If wool is very close, so let me see your list. Yeah, so it's Probably not made of any of these things, though, right? Okay, can I hear some explanations? What do you guys think is happening? What do you think? Okay. Okay. So there's some good things said there. One thing that's missing though is if, let's say, I'm rubbing my feet along the floor and I'm charging my wool socks, my socks are becoming positive, what's happening to the rest of me? Especially my hands, which are on the opposite extremities of my legs. They're becoming more positive or more negative? So imagine this. So my socks are positive, all right? And it has the ability to attract the electrons from everywhere inside of me. So it's going to pull the electrons down to my socks, and my hands are going to become positive. Exactly, yeah. So, so now my hands are positive, and I'm approaching my styrofoam thing, all right? And the styrofoam things are getting attracted to me. So could you repeat what you said about that? So how did they get attracted to my hand? Yeah. Okay. Yeah, absolutely. So what's going to happen is your hand is going to induce a charge in the styrofoam, right? So it's going to push away the protons, or rather, it's going to attract the electrons, and it's going to attract the electrons in the styrofoam are going to get attracted to your positively charged hand. Now, what is styrofoam? An insulator or a conductor? It's an insulator, absolutely, it's an insulator. And how does that explain the fact that the styrofoam sticks to your hand and doesn't just stick to your hand and then pop back off? So why isn't it that the styrofoam comes to you and sticks there rather than it comes to you and it bounces right off you after it gets your exposure? So again, what's the definition of an insulator versus a conductor? Yeah. Okay, so charges don't move through an insulator. So I would guess, I mean, again, none of this really has an answer, but I would rationalize that because it's an insulator, then it would contact your hand, and because it's being attracted, it's fine. But since it's such a strong insulator, the charges aren't transferring at a very rapid rate. So it'll stick to your hand for a longer period of time before falling off. Right? What could you do to prevent this from happening? Now, the answers I got yesterday were silly. They're like, well, don't wear wool socks. But you love your wool socks. It's Christmas. It's tradition. You have to wear them. So what do you do to circumvent that? So without changing your socks, without recarpeting your house, what would you do? Yeah, exactly. You would ground yourself. So you would touch some metal object or some conductive object that's attached to the ground, and you would discharge or recharge any kind of imbalance of charges that you have, and then you become neutral, and you could open your gifts hassle free. Yeah. It's not that it itself can have its electrons move inside, but it's not going to distribute evenly. That's what makes it an insulator. So you would touch it, it wouldn't take your charge, or it would take your charge, but it would take it very slowly, and then during that time it's being attracted. And eventually, once it falls off, then it would be charged, but not so much. Okay. So next we talked about electroscopes and Coulomb's law. So electroscopes, if you remember, is that device where if I brought something charged next to it, the two leaves separated. So remember, there might be any kind of theory behind what's going to happen if I touch this, if I bring this closer. So let's just do an example right now. If I brought a charged object close to my electroscope without touching it, what happens to the leaves? Do they spread apart? What happens? You tell me. So I bring a charged object next to my electroscope without touching it. The leaves will spread apart, and then if I move my charged object away, okay? And what happens if I would touch my electroscope with my charged object? Yep. Yeah, they would stay repelled. So your electroscope would take in your charge and, well, permanently, I mean, obviously nothing is permanent because of imperfections, but it would stay apart for good. Okay. The reason why there is all this repulsion and attraction is because of Coulomb's law. Okay, and Coulomb's law states that opposite charges repel each other, opposite charges attract each other, similar charges repel each other, and that this force is quantifiable through this equation here. Okay, and if you remember, this equation is very simple to use, but at the same time, it's important to know when it can be used. Okay? It cannot be used for any charged object. This is only for point charges. Point charge only. Okay? And if you want this to be, if you want to apply this to anything bigger than a point charge, you would start to have to use integration. Now, what does it mean to be a point charge? Well, it's ambiguous, right? If I have two points next to each other, okay, that's 2-point charges. If I have a table that's charged and I put a little point charge above it, I cannot use this formula, right? And the reason for that is because my table is not a point charge, and therefore I can't use KQ1. Q1 would be the charge of a point charge. However, if I took that same charge and moved it to the moon, then I can use Coulomb's law because this table is so far from it that it behaves like a point charge. Okay? So you can use this law if you want to compare two non-point charge objects, only if they're really far away from each other. Okay? So if they're close, then you no longer can use it. And while I'm talking about it, if I did have a charge above a table and close to a table, how would I determine the force that it's feeling? Does anyone know that? I mean, we haven't gotten to it yet, but you could use Gauss's law. You can find Gauss's law to find the electric field. And once you find the electric field, then what? So it's not times the distance times the charge. Yeah. So you find the electric field generated from the table, and then you multiply that by the charge, and that's going to be the force that charge is feeling. Okay. Did I explain everything here? Yeah, so it can be used on non-point charges if the distances are great enough. Every formula that's going to have this form, right? So this KQ over R form, and there's 4 of them, can only be applied for point charges. Okay? And again, if you want to use them for bigger things, you have to do integration. So we're going to get to some of those examples. So here's a kind of an application example where I have 2 chlorine atoms. They're charged. What would the charge of a chlorine atom be typically? It's what? The charge, that's the atomic number. It would be what? -1, exactly. Chlorine would be -1. So if I had 2 chlorine atoms, right, and I want to find out what the force is between them, there's a distance of 10 nanometers apart. I can determine what the repulsion force is, right? It's repulsion because they're both negatively charged. Now, there's two ways of answering this question, and I don't care about the chemistry portion. So if you were to consider this to have 8 electrons each, which is what is actually happening here, it has 8 valence electrons each. Or if you wanted to consider that it has only one, I don't really care, right? It doesn't really make a difference. So you can figure out that the force is equal to K times 8Q multiplied by 8Q divided by 10 times 10 to the minus 9 meters squared. Can you guys figure out what's the force on this? Q is going to be equal to 1.6 times 10 to the negative 19. Someone punch this in for me. I don't see anyone using their calculator. Yeah. K is 9 times 10 to the 9. Yeah. Ça change les calculs juste parce que it's more of a chemistry question now. Yeah, I mean, it should kind of make sense. I said 8 because it's following the octet rule. And it normally has 7 valence electrons because it's negatively charged. It's got one extra one. So you can consider it to be the one extra one that you're measuring or the 8 that it has in total. Okay. So do I have a number? Yes, no, maybe. Okay, well, doesn't matter what the number is. Let's move on. Next, we did electric field, and we also learned about how to draw electric field lines. And the convention was that whenever you draw an electric field line, you draw your arrow from your positive to your negative charge. Is that right? Positive to negative charge? Yeah, exactly. Positive to negative charge. And that the direction of the arrow, what did it indicate? If I had an electric field line going from my positive to my negative, why did I draw that? What's the convention? Exactly. It's the direct positive charge of good to place it in that electric field. All right, so that's how you determine that one. This value that you're measuring, right, this electric field value, is the theoretical force that that would exhibit on one single charge at any place where there is an electric field. All right, and because of that, electric field is a vector, and therefore it cannot have two different directions at a single point. And you need to know that if there is two things influencing the electric field at a certain point, that you need to do vector addition to find out the total electric field at that point. You can find the electric field of a point charge at any distance of a point charge, and it's kq over r squared. And if you want to find the electric field of something more complicated, then you have to use Gauss's law, or you have to use, what's it called, like integration and things like that, or more complicated math to be able to solve. This is, again, only for a point charge, this formula. What you can do, however, is break up a line, let's say, into many point charges, or a ring into many point charges. And in that case, it becomes a lot more simple to solve for the total electric field. You good? All right, so I have a question for you guys. The question is, I have these two charges, This one is placed at -2. This one's placed at +3. And I'm asking you guys, where is it that the electric field in this is going to be 0? So that means that, let's say this was charge 1. Okay. Let's say this is charge 1 and this is charge 2. That means I can say that, what's going on here? I can say that my electric field, sorry, rather, not equal to, but my total electric field is going to be equal to my electric field from 1 plus my electric field from 2, and I want that to be equal to 0. And before I even solve this problem, where is the electric field going to be 0? Is it going to be all the way on the left, in the middle, or all the way on the right? Yeah? On the left, there will be one on the left. There's another one. Where else is there an electric field of 0? In between the two charges, we know that there's one on the left of the charges. Is there going to be one on the right of the charges or in between the charges? The two remaining in between, exactly, right? So if I were to draw my electric field lines, they would kind of look like this. They're both positive charges, so they would go like this. Mm-hmm. Mm-hmm. So there's going to be at some point there, I don't know where, but I just approximately drew a dot there, that where the electric field is going to be 0. And the same thing here, it's going to be, there's going to be some point here. So the one to the left, I'm wondering, it might not be actually, there might not be one to the left. The reason for that is because they're both positive charges. And that means this one here, this arrow here is free to go on forever. So actually there is only one. If there was a negative charge there and then it would deviate backwards, then yes, it would be. Oh, you're right. It would be closer to the 5 to the 10 to the 15. Yeah, absolutely. Okay, so let's solve for this. That means we need to find the individual electric field for each and make it equal to 0. So it's going to be K multiplied by plus 5Q divided by now the distance. So now the distance is going to be somewhere to the right of -2. So I would say that it's going to be -2 plus some distance x squared. And yeah, squared. Or rather minus here. It's going to be minus because it's in the other direction. Minus the electric field from this one. So it's going to be K multiplied by plus 15Q over. And this one is going to be on the left of the 3, so it's going to be minus x. So it's going to be 3 minus x squared, and that's going to be equal to 0. So I'm not going to do this because it's going to take us forever to solve the algebra. We set up the equation. It's one equation, one unknown. Use your math skills to solve it. Yeah. X is the position where it's located, not the distance. questions on this? Next step, solve. Okay. Once we did that, that was all fine and dandy. We did electric field of point charges. Then we moved on to the more complicated electric field of non-point charges. And we introduced the concept of charge density, which is the amount of charges per unit length or unit area or unit volume, depending on what kind of shape we're talking about. Okay, so if it's a wire, it's going to be a charge density per unit length. If it's going to be anything flat, that's two-dimensional, that's going to be per unit area. And if anything's got a three-dimensional shape, then it's going to be per unit volume. Okay. So for example, if I were to ask you what's the charge of a sheet of paper, you would use which one of these three? Which one? Area, exactly. Even though it's theoretically got a volume because it's very thinly thick. If I were to ask you to find the charge of a dice, what would you use? Volume, exactly. Okay. So let's do an example on that. Actually, before I get there, there's two types of problems where I can ask you. One is if it's uniformly charged, meaning that the charge density is not variable, it's a constant. In which case, if this was, if it was uniformly charged, all you have to do is multiply the charge density by its respective unit. So all you have to do is multiply lambda by the length, sigma by the area, and rho by the volume. That's if it's uniformly charged. If it's not uniformly charged, then what you have to do is you have to break it up into really small portions and add them up using integration. So let's do an example of that, where I'm asking you to find the charge of a disk, of a full disk, not a ring, but a disk. And this ring has a radius of 15 meters. It's humongous, apparently. And it's got a charge density that is non-uniform. How do I know this charge density is non-uniform? The what? It changes. It has a variable in it. As long as it has a variable in it, it's not uniform. Okay. So I need to set up my first step of this whole thing is that some small charge dq is, well, not even that actually. Let's start off before that, earlier than this. What we need to know though is that charge is going to be equal to rho multiplied by area. That's the very, sorry, not rho, but sigma. Sigma times area. This is the very basis of this. And if I were to draw my disk that has a radius of 15 meters, right, I can break this up. First of all, if I were to look at my, if I'm looking at my distribution here, what is my charge density dependent on? Yeah, the radius, exactly. So if it's dependent on radius, then let's break my disk up into different radii. Okay? And if I were to break my disk up into radii, what shape am I breaking my disk up into? Rings, exactly. So if I were to bring this up into a ring, and I added up all the rings, then I can get the whole thing. Okay? So if I take one small ring like this that has a radius r, right? Every point along this ring is going to have the same charge because my charge density is dependent on radius only. So this, at one given radius, all of the points along this, along that ring are going to be the same charge, uniform. You can consider that. All right. So that means that my charge for this one ring, dq, is going to be equal to my rho, my sigma as a function of r multiplied by dA. Rho, we know what, sorry, I keep saying rho, but it's sigma. Sigma, we know what it is. It's r squared plus 1.5r minus 10. Now what's dA? What's the area of my tiny ring? Yeah, exactly. So it'd be the, circumference of my ring multiplied by its tiny thickness. What is its tiny thickness? dr, exactly. And that's the charge of my only one ring, and it's not the one I want to know. I want to know the charge of my entire disk, so I'll add them all up. So I'll integrate. So the integral of dq is just going to be q, and the integral of everything else. So the 2 pi ends up being a constant. Integral of r to the 3 plus 1.5 r squared minus 10r dr. And what are going to be the limits of my integral? Yeah, 0 to 15. Yeah. Yeah. Yes. When it's simple, this is a simple one because it's just polynomials. This one you'll have to solve. I have a more difficult one later that we will not have to solve. Yeah. No. Not for integration. I'll give you a sheet before your exam so you can study with it, but not on the exam. All right, I'm not going to solve the integral. It's pretty straightforward. It's the polynomial law. It's going to be something like 2 pi over 4r to the 4 minus plus 2 pi, what is it, 4.5 r to the 3, so on and so forth. It's just the polynomial law. Okay? Any questions? Okay. Next, we came with the electric field of parallel plates, or not even just parallel plates, just plates in general. And this is where we came up with that idea that if you had a flat table that's charged, it's going to produce a uniform electric field. And a uniform electric field is so convenient because that means that no matter where I look at it along the surface, it's going to have the same electric field. This was, I don't remember if you guys remember, but remember we did problems where we had like a charge that was shot in a uniform electric field, and we're looking at its trajectory and how its trajectory changed. This was that section of the course, okay? And we figured out that we can find the force acting on a charge if we were to just multiply the electric field by the charge. Go back to your notes there, and if you want to figure out the derivation of this. It's not quite important as much as it is how to use it. And of course, because it's a force, it's always going to be equal to m times a. So I have an example here. An electron is launched, I wrote vertically, but I actually meant horizontally. I launch an electron horizontally into a uniform electric field. It's important that it's uniform, otherwise we wouldn't be able to do this kind of problem. The acceleration in this, if the electric field were changing, then the acceleration would also be changing, and we've never learned the math to do that. So we're not going to deal with a non-uniform electric field in this kind of problem. It has a velocity of 3.4 times 10 to the 6 meters per second. There's a length that is 20 centimeters. I want to just say that I don't know if this is true or not, but I just want to say it. If we will assume that this speed here is fast enough that it's never going to collide with the plates here. We're going to assume that it goes through the whole thing. If you want it to be really thorough, you can check to see if it does collide with it. But I don't really want to deal with that. That's not the point of this problem. Someone pointed that out yesterday. I was like, you're right, I didn't think about it. But let's just ignore that for this. All right, so, sorry, Zach. I have an electron in an electric field, right? Is it going to go in the same direction as the electric field lines or in the opposite direction of the electric field lines? Opposite, exactly. This is an electron. It's going to feel an acceleration upwards, right? So my force, my electrostatic force is going to be upwards. Okay. Initially speaking, does my velocity have a y component to it? No. Initially, it's only got an x component to it, and the acceleration is happening in the x axis or in the y axis? In the y-axis. So does my x-axis velocity change? No. Initial x velocity is the same as my final x velocity. So if I have some velocity here, v1, and I want to find out what my total velocity is at the end, this is going to be my y and this is going to be my x. This component, vx, is not going to change. It's always going to be 3.4 times 10 to the 6. Remember, that's one of Newton's laws, that it won't change unless there's an external force acting on it. There's no force acting on it, therefore my velocity doesn't change. And now my question is, well, I need to find this direction here, this angle, and I want to find the magnitude of my v total at the end. That's what I'm asking. So if I want to find my v total and I have my vx, what piece of information am I missing? Missing what? A and t. In order to find what though? What am I looking for? Not displacement, I'm just looking at the angle. So here's my Vx. What I need is, what's going to be here? Yep. Yeah, I need my Vy. And in order to find my Vy, I need my time and my acceleration. Okay. So acceleration, that one's easy to find, right? We've just looked at an equation before. QE is equal to ma, and therefore QE over m is equal to a. And we can say, we know the charge of an electron is 1.6 times 10 to the negative 19 coulombs, multiplied by the electric field, which is 15 newtons per coulomb, divided by the mass, which is 9.1 times 10 to the negative 31 kilograms. Can someone give me a value quick for this? Should be a big number. 1.6 times 10 to the 12. 2.6, you said? Okay. Units? Meters per second squared, because it's accelerating. I want to pose you guys a question of significant figures. How many significant figures does this have? Nope. How many? It's a constant. It's got infinity significance. Okay. How about this one? Infinity. This one? 2. Okay. So this is the reason why I have two sig figs, not because of this and this. Right? Whenever I have a constant, something that's not measured and is given to me, right? That is going to be a constant. Okay. Great. I have my acceleration. What was the other thing you said I needed, Cedric? Time, exactly. So how do I figure out time? Yeah. Uniform accelerated motion? Mm-hmm. You could use, no, actually you can't even use that. You don't have your Vy. You can use it very simply by looking at the x direction, right? So no acceleration motion. So if this has no acceleration coming here, then if you have the velocity of how long it takes to do 20 centimeters, then you have the time, right? How long does it take an object going at 20 kilometers an hour to do 20 kilometers? It takes 1 hour, right? So let's try that. it's going to be the distance, which is 0.20 meters, divided by the velocity, which is 3.4 times 10 to the 6 meters per second. It's going super fast, and it's not going a big distance. So is the time going to be really fast or really long? Really small or really big time? Really small time. All right, and you guys have a time for me? Negative what? It shouldn't be negative 14 because it's just this divided by this. 5.9 times 10 to the minus 8. Okay, seconds. All right, perfect. I have my acceleration, I have my time. Now I can find my final velocity, because if you remember, it's Vt is equal to At plus Vo. The initial velocity is 0, right? And we're talking about only on the y-axis. So I just need to multiply my acceleration with time. So 2.6 times 10 to the 12 meters per second square, multiplied by 5.9 times 10 to the minus 8 seconds. And that should give me velocity that's 0.5. Someone have an answer for this? Yep. Great. This, I wrote Vt, but this is actually just Vy, or the final y velocity. And that's perfect because now I can use, I have my y, I have my x. How do I find my v total if I have my y and my x? Use what? Trigonometry, or even more simply Pythagoras to find the, and then I have to use trigonometry to find my x. All right? So it would be v total is equal to the square root of vy squared plus vx squared. And my angle is going to be equal to the inverse tan of vy. I think I crashed my PowerPoint. Give it a second. So to find the angle, it's inverse tan of vy over vx. Okay. While this is trying to rectify itself, which you guys should do that calculation. There we go. Vy. And I got a really small angle, I think. Someone find the angle? Let's hear the answers. What'd you get for the angle? All right. I mean, do you guys know how to do this? Do you need me to wait for the answer? Can we move on? Because there is a lot of stuff to go through, and I don't want to dwell on just punching the numbers in the calculator. Are there questions on how I got this? Okay, so let's move on. Did I skip a number? 6 and then 7. Okay, great. All right, so we talked about electric potential now. So now we have electric force and electric field. Now we're introducing electric potential, and the electric potential of a charge, or a point charge, is going to be equal to this to this equation. And remember, again, it's in a KQ over R format, which means that this is going to be only applicable for a point charge. The voltage, or the potential, is the amount of energy that a theoretical charge would have if you were to place it in an area with an electric field, right? And it's not really applicable the way it is right now, because we don't really talk about the electric potential of just one point charge. We usually talk about equipotential lines. But it's still useful to look at this and try to solve it a little bit, because it's important to note that it is not a vector. Okay, that's super important. It's measured in volts or joules per coulomb, and so we can therefore find, let's say if we have 2 point charges, we can find the potential at different points around it. That would be what my example is here. And here I'm asking you to find the potential of this point. Now, do I need to consider any angles in this at all? No, this is not a vector, right? And so therefore we do not consider any angles whatsoever. So my V total, this was 1 and this was 2, would simply be the voltage of 1 plus the voltage of 2. Note that there are no arrows above my voltages, and therefore I do not add any angles. Very simple calculation of KQ1 over R1 plus KQ2 over R2. How do I find R? This is R. How do I find that distance R? Yeah, you just use Python. So R in this case is going to be equal to 3 squared plus 4.5 squared, all that square root. Now I have 5 times plus 5q divided by 3.0 squared plus 4.5 squared. For my next expression, do I add it or do I subtract it? I add? Do I add a minus or do I just subtract it? Or how does it work? Does the charge matter? The sign of the charge, does it matter? Some of you are saying yes, some of you are saying no. It does matter, yeah. So it would have to be k negative q, or negative 8q over the square root of 3.0 squared plus 4.5. Term white. Or you could, sorry, I wrote multiplication. Ah. Well, it could be plus minus, or you can just put a minus and take out the minus there. Again, doesn't really matter what the number is. As long as you know how I got to this equation and you know how to use your calculator, you should come up with the right thing. That being said, I'm just going to take a small, like a 10 seconds pause here to ask you guys, is this useful, what we're doing? Do you think this is a good kind of review? Going through the slides, asking questions? Yeah, it's okay? Okay, because we could do it differently if you guys prefer it differently. Because it's going to be a lot of this. Yeah? Okay. Anyone say no? This is boring and I want to go home. Okay, so this, then we talked about equipotential lines. And if you remember, equipotential lines are an infinite number of points where the electric potential is the same everywhere along each of those points on that line. So, so that means that no matter where I go in there, no matter where I put my charge on this equipotential line, it's going to have the same amount of potential energy. And this is when we talked about electric work, and you can see the equation there at the bottom. The potential energy of a charge is going to be equal to QV, all right? And QV is the non-point charge equation. And the KQ1, Q2 is the point charge equation. And as soon as we talk about energy or potential energy, you have to think about, okay, if it's potential energy, then that energy can become something else. When we're doing this problem, these problems, our potential energy most of the time was becoming kinetic energy, right? Or the change in potential energy gave us change in kinetic energy. So the change in potential energy gave us the change in kinetic energy. Ultimately, what you can do is say 1/2 m delta V squared is equal to Q delta V. Yeah. Yeah. Yeah, you would never use it as regular Q times V, because you would always, like, if you were to use Q just V, you would assume that your final potential is zero. Kind of like when we did potential energy or gravitational potential energy, we use mgh, not mg delta h. But in reality, it's mg delta h. So remember, always when you're talking about energy, always remember the idea of conservation of energy. If your energy is escaped somewhere, then it needs to go somewhere else. If you're losing potential energy, that means you're gaining kinetic energy. If you're gaining potential energy, that means you're losing kinetic energy, right? And that's all assuming that there is no friction or anything like that, or energy loss is heat. But the point is that there is this imbalance between these two types of energy, kinetic energy and potential energy. If I were to take a proton and move it to an area of a positive potential, right? So let's say I have 10 volts here and 20 volts here, and I have a proton that I want to move in this direction. Is that going to require energy, or is that going to release energy? What do you think? It's going to require energy because it's going to an area that's more positive. A positive charge going into an area that's more positive is going to require energy. So is it going to gain potential energy, or is it going to gain kinetic energy? It's going to gain potential energy, okay? And so therefore, if it's gaining potential energy, that means it's losing kinetic energy, okay? Because that energy has to come from somewhere. What if it were an electron doing the same thing? Would it gain kinetic energy or gain potential energy? It would gain kinetic energy. It's going to an area of higher potential, so therefore it's going to become faster and faster. It's going to want to go there. So let's do this problem. Proton is taken from point A to point B. If it had an initial velocity of blah, what is its final velocity? And then what if it were an electron instead of a proton? So my proton starts off there, ends up there. What's my change in voltage? 40 volts, right? So from 30 to minus 10, that means there's a delta V of 40 volts. And whether I take this trajectory or this trajectory, is my delta V the same? Yeah, so it doesn't matter. My answer is going to be the same regardless of which trajectory it takes. the energy change is going to be the same. If it were a real world situation, doing this is probably going to release a lot more energy as heat, but we're not dealing with realistic situations. Yeah, you can say it's minus 40, but mathematically we're going to disregard that as long as you keep in mind that you're going to, is this going to be proton going to gain kinetic energy or lose kinetic energy? So you just need to know that your potential energy is going to become kinetic energy. Yeah, okay? You don't need to consider that it's a loss of potential. So in my equation here, I can write down that I had an initial kinetic energy and I had some initial potential energy. And that gave rise to some kind of final kinetic energy. And at the end, I had no more potential energy because that's where I stopped. It's going to be my change in potential energy is going to be based on this. So I have 1/2 mv initial squared plus q delta v is equal to 1/2 mv final squared. Alternatively, I can write it a different way. If I were to bring, am I going too fast? Okay. I'll take a 10-second pause for you guys to catch up. If I were to change this around and move this 1/2 v initial squared, if I were to move it onto the other side, right? So if I were to take this, bring it here, I would be writing q delta v is equal to 1/2 m vf minus vi squared, right? And this here is just the change in velocity, or delta v, small v. So sometimes I might ask you what is its final velocity. Sometimes I might ask you what is the change in velocity. You can use whichever method you want. Just don't get confused between the two. Okay? Again, not so worked up on the numbers. What do I need to do differently if this were an electron? So this is for a proton, and now an electron. What would I do differently? Set up this equation for me here. This first equation. How would I set that up? Yeah? Yeah? Exactly. So it would have final potential energy plus final kinetic energy. So with an electron, would it be slowing down? See that? An electron going from high to low voltage, it would be slowing down because it's going into an area that's more negative. Any questions on this? All right. Gauss's law. So if you remember, Gauss's law has, initially when we were first introduced to Gauss's law, it was about flux. Who can define flux for me? Yeah, exactly. The amount of electric field lines through an area is the definition of flux. So that means that electric field, E, is important and that the area is important. So A is also important. And in the cases that we looked at when we're doing Gauss's law, we always chose a Gaussian surface such that it met two conditions, all right? The two conditions were that there is an equal distance everywhere to the charged object, and two, that the area and the electric field were always parallel, okay? So if those two conditions were met, then I can just say that my flux is equal to just E times A. And that's a lot more simple than using E dot dA and then doing the surface integral of that, right? What we also noticed was that we had this relationship, right? That our flux was directly proportional to the charge enclosed, right? That the flux is directly proportional to the charge enclosed, right? So if I made a Gaussian surface around a charge, then I could find the flux coming out of that surface. We're going to do a lot of examples. I put 3 examples of Gauss's law because this was an area that you guys had trouble with when we were doing it. So I want to make sure that we remember and understand this stuff. So I'm telling you here that the inner sphere has a charge of plus 3q. This is minus 5q. It's not, you can't see it here. Let me just move this out of the way. This is an insulator. That's an insulator and that's a conductor. That's going to matter. Okay, the fact that it's an insulator and a conductor is going to matter. So let's draw a graph. There's 4 areas that we need to consider. The areas are from the center to the end of this insulating sphere, this empty space in between the 2 spheres, the mass part of the hollow sphere, and then everything outside of both spheres, the 2 concentric spheres. Okay? This is a classic exam question. So again, if I want to ask for a reminder, what does it mean that I have a charged insulating sphere? Charges are what? Charges don't move within the material. Contrast this to a conductive sphere. What would have happened if I had a conductive sphere instead? What could you say about the charges on a conducting sphere? Exactly. So on a conducting sphere, because the charges are allowed to move, they're going to move and spread apart as much as possible and therefore be concentrated only on the outer layer of the sphere. Because it's an insulating sphere, you can assume that it's uniformly charged unless otherwise specified. So if it's uniformly charged, then that means there's charges in the middle and there's charges in the center and around the edges, wherever, along that insulating sphere, there's going to be charges everywhere. So let's take a Gaussian surface right there, right? And here, if I choose it correctly, I can find out my electric field. So we're trying to chart electric field as a function of distance. So my electric field is going to be Q enclosed divided by epsilon naught times A. So in my little Gaussian surface, is there a non-zero amount of charge enclosed? Yeah, there is, right? There is, if I take a Gaussian surface here, then there's some charges in between the center and the edge of that little Gaussian sphere that I chose. All right, if I were to take a bigger one, do I have more charges enclosed now? Yeah, I do. And if I took the whole thing, do I have more charges enclosed? Yeah, absolutely. All right. So then that means that my charge enclosed is increasing with respect to time. Therefore, and because my charge enclosed and my electric field are directly proportional, I can say that my electric field is increasing with respect to time. So we can draw something like that. I take a Gaussian surface out here versus a Gaussian surface out here. Does my charge enclosed change? Does my charge enclosed change? No. So my charge enclosed is always going to be equivalent of the charge inside, which is 3q. All right, so my 3q doesn't change, but now my r is changing, right? Because I'm getting further and further away from a spherical charge. So that means now I'm going to have a decreasing trend of electric field. So it's going to look something like this, minus the jittery hands. Let me try that again. Okay. This outer sphere here is made of conductive material, which means that charges are allowed to move through it. So where are my charges going to be located? Where? On the outer edge, the inner edge, or both? Okay? Both, exactly. And the reason for it being both is because there is a charged sphere on the inside. If there was no charged sphere on the inside, then all the charges would be on the outer edge. But because there's a plus 3q here, how did that happen? Because there's a plus 3q here, that means there's going to be a what charge along the inner edge of this sphere? Minus 3q. So if I were to take a Gaussian surface right there, what's my charge enclosed? 0, exactly, because it's minus 3q from the inner surface of that outer shell, and my plus 3q of my inner sphere. And if my net charge inside, therefore, is 0, if my q enclosed is 0, then my electric field is 0. So that means all along here, my electric field is going to be 0. Yeah. If I'm here, let's say, it's on the inner surface and on the outer surface. Anything in between is considered to be no charge because it's conducting sphere. If it was an insulating sphere, then it would be different. What's the charge on the outer surface of this sphere? Minus 2q. Okay, that's going to be, I have 3 of my minus 5q's are there, and so the rest of my charge is going to be on the outside. So this is going to have a minus 2q charge, and everywhere I look on the inside of the Gaussian surface, if I place it outside, it's going to encompass something that's got a net charge of minus 2. So my charge is not changing, but my distance is, and therefore I should have something like this. And the reason why it's upside down, it's because it's a negative charge instead of a positive charge. concept question is, here we drew a diagram that had a -5 charge outer hollow sphere. What if this was +3 and this was +5? Okay, so this is +3, this is +5. Okay, what would the charge on the inner surface of this sphere be? 0? Not 0. So this is +3. This has to be -3. Okay? And if this is -3, then what's the outer surface? 8 +8. Okay? Remember, it's not how many charges you have, it's what is the difference in charges. Because you're going to have a seemingly infinite number of charges in something like this. And it's really just the difference in charges that create a charge. So just because it's 5q or +5q doesn't mean it has no electrons in that whole thing. Of course it has electrons. It's just there's a net positive charge. Any questions on that? Okay, let's do another example of Gauss's law. It says magnetic field here, actually, so that's wrong. It's an electric field. So determine the electric field at a point 5 centimeters away from a uniformly charged wire with a length of 11.7 meters and a charge density of that. Now, is the charge density uniform or not? It is uniform, right? You have a question, Zach? It has a length of this, and the charge density is along the length of the wire. Yeah. Yeah. So let's draw this. I have my wire, 11.7 meters, and some point above it at 5.0 centimeters. I have to use Gauss's law here. And so that means I have to pick a Gaussian surface. And what is the shape of my Gaussian surface going to be? Yeah, a cylinder. You want to be more specific about what kind of cylinder? Is it like a full cylinder, a hollow toilet paper-like cylinder, or is it like a cylinder with surfaces on either end? Option B, toilet paper cylinder. All right, this is going to be a toilet paper cylinder roll. So that means if I chose a Gaussian surface that goes, if I chose a Gaussian surface that went through my point as such, I know what the radius of my Gaussian surface is because I chose it to be at 5 centimeters away from my wire. And now I can easily apply the Gauss's law. Gauss's law is E times A is equal to Q enclosed over epsilon naught. And if I'm looking for the electric field, I can say that Q over epsilon naught times A, where A is the area of my toilet paper roll, of my Gaussian surface. How do I find my Q? Yeah. You say that again? Exactly. So lambda L over E naught. And how do I find my area? What kind of area is it? It's a what? It would be the area of my cylinder, not my wire. It's a toilet paper. How would I find the area of a toilet paper roll? Yeah. Exactly, the circumference times the length. If I were to cut my toilet paper, it becomes just a rectangle. One side of my rectangle is the circumference, and the other side is going to be the length. So it's going to be 2 pi RL. Look, my L is not even important in this problem. So now my electric field is going to be equal to lambda over epsilon naught 2 pi r. And r, remember, is my 5 centimeters. Let's do one more Gauss's law example, and then we'll take a break, and then we'll go on to circuits. So I have an insulating cylinder with a radius of 4 centimeters and a height of 16 centimeters with a charge distribution of whatever that is. Determine the electric field at a distance of 1 centimeter from the center of the cylinder. So if I were to draw this, it's not a toilet paper this time, it's a full-on cylinder that's full everywhere, all right? And it has a radius of 4 centimeters. And I'm trying to determine, this was the center here, at this point, what is the electric field? And this point has a distance of 1 centimeter. What would be the electric field there? So I could use Gauss's law again, but this time I don't think I can avoid using integration. So I have to draw a Gaussian surface. Like that. And I can set up my Gauss's law as E dot dA is equal to Q inside over epsilon naught. What's my charge enclosed if it's a volume? It would be rho times volume, exactly. So it has the integral of E dA is equal to rho times volume over epsilon naught. Is my electric field uniform at that point? Is my electric field uniform at this point? Yeah, so I can take it out of the integral. Is my area a nice shaped area? So I can remove this here and change it to E times A. Okay. And so I can rewrite this as rho V over epsilon naught times A is equal to E. But that's not simple because my charge distribution is not uniform. So I do have to do some integration. So what I can do is I can write rho as a function of r multiplied by dv over epsilon naught times A is equal to dE. The electric field at this point, this tiny point, right, is going to be proportional to my to the integral of my charge distribution and that tiny volume. All the tiny volumes inside of it. So let's rewrite everything. my rho is 1 over, give myself more space, 1 over 1 minus r multiplied by my d. What's the volume of my small toilet paper that I'm making up this big toilet paper, thick toilet paper roll? Is it? Yeah, area times, not length, but area times the thickness. Okay, so what's the area of my toilet paper roll here? 2 pi r L. We talked about it just before. So 2 pi r L. And the thickness is going to be times dr. So now I have my volume of my toilet paper roll. All this divided by epsilon naught, and all this divided by the area of my Gaussian surface. Yeah, Elizabeth? I went from here because this is if everything was perfect and uniform, I could use this. But because it's not perfect and uniform, I have to add up all the little non-perfect parts to get up to the big full thing. All right, that's how I went from there to there. So I changed this from rho v to rho dv so I can get my dE. So I can find my area of my toilet paper roll. We talked about that again. It's 2 pi r. No. Is it 2 pi? Is it not the same r at this point? It would be 2 pi capital R. Oh. And that's equal to dE. Yeah. Yeah, 1, exactly. And little r is all the radii of all the little toilet papers that are making up my Gaussian cylinder. Now I just need to integrate this. So the integral of dE is just E, and I can take out all my constants. Well, 2 pi is going to cancel out. My L is going to cancel out. It's going to be R over 1 minus R dr, and that's the integral. And I can take out my only constant, which is epsilon naught. Yeah. Oh, you're right. So now it just looks ugly. Let me just rewrite this. Yeah. Okay. Yeah. Yep. Exactly. So in this case, which are my limits of my integral? It would be 0 to 1 or 4? Yeah? 1? Yeah, 1. All right. The limits of my integral is 0 to 1. Or 0.01 because it's in centimeters. All right. Long story short, the integral of this is going to be ln of r minus r multiplied by your constants, 1 over r epsilon naught. When I was writing this, I didn't really pay attention to how hard of an integral this is going to be. So this is a little bit above the level of integration that you would do for the exam. I won't ask you to do something this complicated in terms of integration. The problem itself, setting up the integral, that's fair game. It's the integration itself, it won't be this one. Okay? And this one is going to be integration by substitution, if you're curious. Okay, let's take a break. Come back in 5 minutes. problem. So what you missed was just review, and I'm going to post this up. It's already posted up. You can just pull it up. But with my notes, you can see it posted up. And this is what we're doing all of today and all of next class.
And for the first development topic, I have a code. How do I give you the presentation?
The code. Do you have a physical project then?
Yeah, I do have my code.
I don't need to see the code.
Oh, you don't need to?
Because I'm not your programming teacher. I won't even understand it even if you show me.
Okay.
Yeah.
And
Okay. Yeah.
it takes forever to download the video on YouTube, so is it okay if I get it later today?
The video is due at midnight tonight.
Okay, okay.
Yeah.
Thank you.
Hold on to it for now. What did you want to turn it? What kind of wire did you use for the project? Was it when is your project due for programming? That'll be done by then. Yeah, Zach? Zach, you have a question? Yeah, as long as there's one in your document. Yeah. All right, let's get started again. Um, I don't have any problems on capacitors, but there is some basic concepts that you have to remember about capacitors. One is that capacitors store charge, aka also energy. All right, charge and energy don't mean the same thing, but by storing charge, you're essentially storing energy. All right, and it's able to discharge that at a time's notice in a circuit, however you want. The point is though that you can increase the strength of your capacitor by making a better insulator in between. What was that material called again? You guys remember? Yeah. Exactly. So you have to remember that the dielectric in the middle is what determines how good a capacitor is. Also, how big the area is and how little the distance between them is. Okay? So the more you change these variables, you can change the functionality of the capacitor. I'm not going to go into it more than that, other than it can hold a charge for a long time. Okay? So that's like really the take-home message of this, is that it holds a charge. Yeah, no problems on this. Any questions on capacitors, things that you might not remember? Yeah. Yeah. So the charge has nowhere to go. So if the charge has nowhere to go, the charge stays the same. Capacitance changes. So how does that affect voltage? Yeah. Okay. All right. So we have the first lesson on circuits now. It goes from 10 to 11. And the reason why, sorry, from 10 to 12, the reason for that is because 11 is was a review that we did for test one. So there was nothing that we learned for that, which is true. So we went straight to PowerPoint 12, which is the first lesson that we did on circuits. The continuous flow of charge through a wire, which we call a current. And we were introduced to Kirchhoff's laws, which there were two of them. One of them was about voltage and how voltage stays the same for parallel portions of a circuit and drops for the series portions. And it's the opposite for current. And current stays the same for the series part of a circuit and splits up when you're talking about the parallel portion. There's also these equations that we learned about resistance, how we add them up and see them in parallel. I think you guys are very, very familiar with that. But even, let's say you're not, let's try this as a practice. Try to do this, try to find the equivalent resistance of this circuit here. The pros will do this in their head. Yeah. Do I have an answer? How much? 3. Which resistor did you add first? The 2 4s, you're going to add these two together, theoretically, yeah. And then what? These two together, these are in series. And then you would add all of these together. If you add all of these together, you get an equivalent resistance of 1 ohm. And so that puts it in series with 2, 1, and 3. So that would be 6. And that 6 with this 6 in parallel would give you a 3 overall. There is a different way of looking at this, though. I just want to point your attention real quick to something. If I were to combine these two into a 2 ohm resistor, what would be the relationship between that 2 ohm resistor and this and this? Are they all in parallel together, or are these two parallel together and then that is in parallel with this? Or does it not make a difference? Zach, what do you think? They're all parallel to each other, right? So when a current comes in here and it comes at this node, it's got 3 options. 1 option, 2 options, 3 options, right? So they're all in parallel together. You can do 1 over 4 plus 1 over 4 plus 1 over 2, it gives you 1. Or you can do these two first and then add this one in parallel. It ends up being the same thing when they're all in parallel. Okay? Perfect, we'll move on. Ohm's law. Now we're talking about measuring that current, measuring that voltage, the relationship between voltage, current, and resistance. And if there's less resistance, there's going to be more current, right? So imagine you're trying to run fast, and there's someone pushing against you, and that person is the resistance, and you're going to run less fast if there's more resistance, and you're going to run more fast if there's less resistance. It's logical in that sense. Now, if I had a parallel circuit where I had 2 amps coming in, and the value of my 2 resistors were, let's say, 0.0000001 and 100 ohms, what would the current distribution look like? And I'm not asking for actual numbers, but what would the current distribution, the 2 amps, how would they distribute between those two? Yeah, most of it is going to go to the top one. So it's going to be like 1.9999 of my 2 amps is going to go to the top one because there is less resistance there. But is there going to be a current here? Yeah, absolutely, there's going to be a current there. All right. The only way that there would be no current here at all is if the resistance of this top one was what? 0. All right. If this had a 0 ohm resistance, then all the current would go up and none of the current would go down. Questions on this? Let's do that same problem that we did before. Try to find the current passing through this 4 ohm resistor. Go. So remind you that it was Req of 3 ohm. There's a strong citrus. Yep. 1 amp, close, not quite. Yep. 0.5. What is the equivalent resistance of all this here? 6. And this one is also 6, which means that if I have, well, let's find out my total current. My total current is this divided by 3 amps is equal to, 3 ohms is equal to 4 amps. So that means here I have 4 amps of current. 4 amps of current, which means I have 2 amps there and 2 amps there, right? They're equal resistance. This branch and everything else is an equal resistance, so there's going to be 2 amps going down, 2 amps going right. Then it comes up to this junction here. What's the current of this junction here? It's also 2, right? And now it's going to split amongst 3 different directions, and you can find it through proportions, or you can find the voltage drop here. If you want to find the voltage drop here, what would be the voltage across this big circle that I drew here? Would be what? What's the voltage across my big circle here? 12, exactly, because it's in parallel with this. So it's going to be 12 volts. And you can find the voltage drop of each of these, right? Because you have a current of 2 amps. So this is going to have a 4 volt drop. This is going to have a 6 volt drop. And therefore, there's going to be a 2 volt drop for this, right? So that means this is going to have 2 volts. And if it has 2 volts, then it means it has 0.5 amps. Any questions on that? All right. Moving on, we talked about diodes. There's some very basic theoretical principles on diodes that's important. One is that they only allow current to go in one direction. Right? You can use that to your advantage to rectify an AC current, making it into a DC current. You can refer to the direction of the diode's placement by saying reverse bias or forward bias. So if it allows it to go forward, it's forward bias. If it prevents it from going forward because it's not allowing it, then you call that reverse bias. There is a voltage at which you can destroy your diode, right? So if you have it in a reverse direction, it doesn't mean that you can put a one reverse bias diode in front of the Hydro-Quebec Dam and then the whole city is not going to get electricity. There is a voltage that's going to cause your LED to not function anymore. That's called the peak inverse voltage, right? You have to remember that it's non-ohmic, which means that you cannot use V is equal to IR. You cannot use this relationship for diodes, right? It has a resistance, but it doesn't follow the same relationship with voltage and current as regular resistors. The reason why we end up burning all our LEDs is because the resistance is so low that the current becomes really high. That's why you can't put it in a circuit without a resistor in front of it. The resistance is actually really, really low. Even though the voltage is like 3.3 volts, you would think that the current is normal, but it's actually not. The resistance is quite low, and therefore the current passing through it is quite high. That busts your LED. We talked about batteries, how batteries, when you put them in series, they add up. You add up the voltages. When you add up so when you put them in parallel, you do not add up the voltages, but you can add up the currents, or you can split the current, such that each battery is working less. Also, we talked about batteries. When you add a battery in parallel, it does not affect the brightness. When you add up the light bulb in series, it does affect the brightness. Okay, and I have a problem that you guys can work on. It's determine the tendency of the brightness of the light bulb from left to right. So what's happening to this indicator light bulb as I'm adding more light bulbs in parallel? So what's happening to my indicator light bulb? Increases? Yeah, absolutely. As I add more light bulbs or add more resistors in parallel, I'm decreasing my REQ. And when my REQ gets lower, my amperage gets higher. And this light bulb is in series with the battery, so it directly affects the brightness of this light bulb. So as you decrease the resistance, you're increasing the current through the light bulb, therefore increasing the brightness. So this one increases. I have a follow-up question for you. What's happening to this light bulb as you add more and more? Right, so let's assume that that's always the same light bulb there. What's happening to that light bulb as you add more light bulbs in parallel? Stays the same, exactly, right? So this one stays the same. Okay. So we have loop circuits. This one you guys are very well familiar with. The only one thing I want to explain on this is, first of all, yes, there will be a question where you will have to solve the matrix on the exam. So make sure you know how to do the additions and all that stuff. Another thing I needed to just mention real quick is I think there was some unclarity based on the orientation of the batteries. So in this case, let's say this is one of my loops, and my loop is in this direction. Sorry guys, I'm in class right now. Thank you. Of course it doesn't give a shit. So let's say this was 9 volts, this was 3 volts, and this was 6 volts, and this was 20 ohms, right? And I had to write down the equation for this. What would the equation look like for the loop for this question? So take a minute to do it, and then read it to me. A lot of noise out here, guys. So let's go in order. Let's start with, let's say, this 3-volt battery. What do I do with that 3-volt battery? Add or subtract? Add it. So plus 3 volts. Then the 9 volts. What do I do with that? Add or subtract? Add it. Then I get my 20 ohm resistor. Add or subtract? Subtract 20 ohms multiplied by the current in this loop. All right. And then I'm at the 6 volts. Do I add or subtract? Subtract, because my battery's plugged in the wrong direction. And all that is equal to 0. All right. It has to be equal to 0. That's what the loop rule is. That within a given loop, your voltage gains and voltage drops all going to add up to give you 0. So here I'm going to end up with plus 3 plus 9 minus 6, which is just going to be 6 volts minus 20 I is equal to 0. Okay? Okay, Wheatstone bridges. I'm not going to give you an example of a Wheatstone bridge because we've done this to death and there's really only 1 or 2 ways of doing it. Essentially, what you need to remember is that a balanced Wheatstone bridge, for God's sake. Guys, I'm in a class. Please be quiet. In a first years, brilliant. What you need to remember that in a balanced circuit, you can apply this relationship across the bridge. And that means if I have a balanced circuit, I'll explain what that means. I don't even need to write anything there actually in the middle. If I were to take the voltage here and here, let's call this voltage A, voltage B, and the voltage AB, if it's equal to 0, even if I put a wire there would be no current at all whatsoever. Right? Even if that wire had no resistance, there would be no current in it. And the reason for that is because the voltage across A and B are exactly equal, and there is no drive, there's no force pushing charges through that wire, okay? And when that's true, you can apply this relationship here. If this was R1, this is R2, this is R3, and this is R4, all right? That's when it's called to be a balanced circuit. Last thing that's really important about Wheatstone bridges is that it's an accurate measure of unknown resistors. So if I were to ask in a question, use the most accurate way to determine the value of an unknown resistor, you might tell me to do it in a Wheatstone way, okay? This is more accurate, in fact, than taking your ohm meter and attaching it to your resistor and telling me the resistance that way. Questions on Wheatstone bridges? I have capacitors, and then our C circuits. We'll do 2 more, and then we'll call it a day after that. So we did capacitors standalone before. So now we're doing capacitors in a circuit. And capacitors in a circuit are useful because they can store charge and so on. The use of it most of the time comes when you combine it with something else, not when you have capacitors alone in a circuit. But it's still worth it to take a look at it. These two still apply. It's the amount of charge on a capacitor. If you want to figure out what's the total charge of a circuit, right? So if I want to find the total charge of a circuit, then I need to find the equivalent capacitance multiplied by the total voltage of the battery on that circuit, right? So it's the same relationship. You can apply it as small or as big as you want. And then you can also see, using that relationship, you can see what the energy stored in an entire circuit is by doing something like this. Can you tell them to shush it? Thank you. What we need to remember, though, is that charges, they add up when they're in parallel, right? So if I have two capacitors like this, those two charges are going to add up, versus if I had this, my charges do not add up. It's the same charge for both of them, okay? So this one you can say Q total is equal to Q1 plus Q2, and here you can say that Q total is equal to Q1 is equal to Q2. Remember, if I want to find the total equivalent capacitance for series, I got to do it the opposite. So it's 1 over C1 plus 1 over C2, da 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 da. This is for series. And for parallel, it's CT or is equal to C1 plus C2, et cetera, et cetera. That's for parallel. All right. So two things. I want you guys to determine the total charge on this circuit. And lastly, I want you guys to figure out what the charge is on that indicated capacitor. Oh, and the voltage is 120 volts. Can someone do the CEQ in their head? What's the CEQ? 2. The total charge in this case would be my total capacitance multiplied by my total voltage, which would be 2 microfarads times 120 volts. That's going to be 240 microcoulombs. I could also say that it's 0.240 times 10 to the, or actually remove that last zero actually, times 10 to the minus 6, 3. Cool. How would I find the charge on each of my capacitors? I thought I know that, yeah, the charge. I need to find the voltage across each of my capacitors. So this one, and everything here is in series, right? This, and this, these three are all in series. There's an easy way of doing this one because the numbers are really nice. What's the total equivalent capacitance of all this? 6. And if it's 6, 6, 6, that means there is an equal voltage for each of these, which is 40. That's the nice, easy way of doing it because our numbers are nice. If it wasn't that nice, I can find that because this, all this, and this are in series, that means their charges are all the same. And if their charges are all the same, and I know their equivalent capacitances, then I can find the voltage across each one. Okay? So let's just, we'll do it the quick way for now. It's going to be 40 volts here, 40 volts here, and this whole thing is also going to be 40 volts. All right. So here it's going to be 40 volts. This 40 volts needs to be separated into how many parts? So there's going to be this branch, and what the voltage here is going to be 40, and the voltage across everything else is going to be 40 as well. So that means this, and this, or rather, this, and this. 1, 2, and 3, these three are in series. And also, they're all nice and uniform as well, right? 6 microfarads, 6 microfarads, and the equivalent of this is also 6 microfarads. So that means that I have this value divided by 3. So that means here I have 13.3 volts, 13.3 volts, and this whole thing is 13.3 volts. That means the voltage across my capacitor that's indicated here is also 13.3 volts. Once I have my voltage and my capacitance, I can, I can determine the charge. So it's going to be Q is equal to C times V. So that's 4 microfarads multiplied by 13.3 volts. And that's going to be equal to 53.3 microcoulombs. For that capacity. Okay, I'm actually going to, that's a great place to stop. I have to get back your quizzes, and I also want to take your project. So that might take a few minutes.